Hey, welcome to our next talk. It's a talk by Grzegorz from Hazelcast. He will talk about some, CRDT, HyperLogLog stuff, and so on. And I'm passing my word to him. Hello, Grzegorz.
Hello, nice to see you. Nice to see you. Okay, so it's great to see you again. Well, not physically, but mentally. So let's jump right into the session since we don't have that much time. My name is Grzegorz Piwowarek. I work for Hazelcast. I write some articles. I do some trainings, and you can find me on Twitter. Boring part is over. So since we have only 40 minutes of time, I hope during this time I will be able to inspire you about Hazelcast and show that it's not just a simple caching solution, as most of you probably do think about it. If you can feel free to ask questions during the session. I will try to answer them immediately if there is enough time. If not, we'll just move them over to the very last few minutes of the session. Okay, so the story of Hazelcast starts a long time ago in Turkey, around 2008. A simple Java simple caching solution is born. And this is probably what most of you know already, that Hazelcast is some form of an in-memory cache. This is how it started. However, it's 2020. And over the years, the product has expanded a lot to accommodate way more features than ever. So it all started with, indeed, a simple caching solution. But now it's no longer just a cache. It's Hazelcast IMDG, which is an operational in-memory computing platform. Sounds scary? Well, but it's not. So we started with a cache, but over the time we have this in-memory computing platform, in-memory solution that accommodates many multiple clients, supporting multiple languages, multiple paradigms, and not only caching itself. Actually, I would say that caching is one of the most boring options for the Hazelcast itself. So as you can see, there was a cache, but over time, we figured that we developed our open client protocol. Now we support many multiple clients. But if you have a look at APIs and other stuff, you will see that there's way more things that you would expect from the cache itself. And this is pretty much what this talk is about. I want to show you the interesting bits of Hazelcast, the interesting parts, and I'm aware that most of you might actually not need it at all. But still, from a perspective of an engineer that works on some of this stuff, this is still extremely beneficial to understand and learn from. Because by understanding those concept algorithms, data structures, CRDTs, and having looked at how Raft is implemented and other stuff, you can learn a lot. And maybe one day you will actually need it, and here it will be for you. So again, started simple. Now it turns out that in-memory computing is actually used a lot by big companies. So you can see a lot of insurance, financial companies, Apple, Morgan Stanley, London Stock Exchange, JP Morgan Chase, and so on and so on. Because usually those are kind of clients that work on the huge amount of data, but they also need this data to be processed very fast. And this is where Hazelcast fits in pretty nicely. But we not only work with commercial clients, we also work with the whole community. So you can find a lot of integrations with probably your favorite frameworks and other tools out there. Some of them can be quite surprising. You might be using some of the, for example, security frameworks and not even realize that there is a Hazelcast underneath. Let's see. But at the beginning, let's actually try to decipher what IMDG means. IMDG means in-memory data grid. In-memory. In-memory means that effectively that processing is happening, well, in memory, but not in persistent memory, which means that technically if we turn off our node, all the data disappears. But why would we even do that? Because if you have a look at memory hierarchy, you will see that the computation that's performed in volatile memory, this is actually something that can be performed way faster than what can be done with persistent memory. So when we say that it's in memory, it's not like we are complaining, well, we don't really have persistence. No, we are bragging that we can do things pretty fast. By the way, we are working on the persistence mode as well, but that's another story for another time. Data means pretty much that we are computing and storing data. They're simple as that. And grid means effectively that there are multiple processes involved in providing all that functionality. So it's not a single node, it's not a single application that actually computes stuff in memory, but rather a cluster of machines or applications that actually can perform quite complex processing. And as you can, and in most solutions like this, they usually support a client-server mode, which is expected. You deploy a few nodes somewhere, and then you can use a client to connect to it and do whatever you want. However, since Hazelcast is Java first, it features also an embedded mode, which means that you can start a Hazelcast along with your application, inside your application, and they can form a cluster together with other applications that have their own embedded instances. And there are many opinions, but being Java first and having Hazelcast being written in Java, this actually gives quite a lot of benefits for Java developers, but we'll see this in a second. And once you deploy, or once you have a cluster of machines ready, now, of course, you are ready to play along with basic cache access patterns like read through, write behind, and near caching. This is all available out there. However, that's not the most interesting part. So the read through is a simple solution where where your application is not aware of the data source, where it takes data from. It exchanges data directly with Hazelcast, but Hazelcast itself is responsible for loading data from the slow data store that it's in between application and a data store. In this case, you don't need to worry about implementing your own caching logic by yourself. You don't need to think, okay, if we didn't find something in the data store, look up the cluster, and if you're trying to write something, remember to write to a database and then to Hazelcast. No, in this case, this is happening in such a way that it's Hazelcast that deals with reading data through the store on itself. The same can be done the other way around. This is what write through means. So if you write data to a Hazelcast itself, Hazelcast will write the data to a data store itself on its own, without you being aware that the data store even exists. From your point of view, you just connect to Hazelcast. However, as you can imagine, we use caching, to save latency. We use caching because we want to benefit from that. And you might be thinking, okay, but if my normal, typical write to a database is slow, and if I need to write to Hazelcast, which synchronously writes a database, then that will probably take more time. That's how physics work. It will take at least the same amount of time that in the first scenario. And yes, that's absolutely true. However, if you are really after fighting latency on writes, you can use something called write behind, which means that the write to a data store is happened asynchronously after a certain delay that you choose. However, you need to be aware that in such cases, you don't really have 100% guarantees that the write will actually happen. Well, there can be end of the world, all the nodes can crash and this can't happen. But this is a trade-off you need to be aware of and apply consciously. However, the interesting parts happen is that if you want to squeeze even more latency, if your write to read ratio is not well balanced, if there's way more reads than writes, another funny thing is you can actually use a concept called near caching, which means you effectively put another cache on your client side, which means the data that's being fetched quite often can be cached locally by the client to make sure that data is available pretty much for you directly without going to the cluster to fetch data for you. But as you can expect, that's another trade-off, because you might need to sacrifice a bit of consistency in such manner if you want to gain a bit extra points when it comes to latency. Okay, but let's drop caching aside because there's way more interesting stuff in there. So what happens if we want to actually use it? So from perspective of a Java developer, if you want to use embedded mode or client, you just add one dependency, and it's all you need. There is no separate dependency for the client. There's just one that covers both. The reason for this is that client is effectively a very lightweight version of a member, but that's another story. What's pretty interesting is that this is pretty much dependency free. Naturally, there are some dependencies that are not, that doesn't make sense to actually rewrite by yourself. So they are shaded. But the experience from the user point of view is that once you add the Hazelcast artifact, you won't experience dependency hell that you would, that you potentially could. So you can trust it and make sure that it won't pollute your class path with extra dependencies, with transitive dependencies that you wouldn't really want. And this is how you start it. Embedded mode, you just call one instance, the Hazelcast starts, and you're ready to use. Same with the client server, looks similar, and that's all. Obviously, this works a bit different for every different client and every different usage that will behave a bit differently. However, the philosophy is pretty similar. Okay, so how does it look like? So usually once you start the instance, now you can get access to data structures like an IMAP, and put and get data just like you would with any other map. And this actually works. This puts and stores data to the cluster itself. The interesting part, however, is that most of those data structures, they actually implement Java util interfaces. So if you want to store it, so as simple as it can be, if you know how to interact with Java util map, you probably know how to interact with the Hazelcast's distributed map all over the place. But this is where the magic happens, because it might look like you are just storing and taking data from a simple map, but underneath there's magic happening. So from your point of view, it's just a map.getFree. You get a pair of values. But what's really happening? This data is actually evenly distributed, partitioned among the whole cluster. So there is no a single map being stored in memory, just chunks of it. So actually there's so this is just a whole cluster encapsulated by one single interface. And map is just the beginning, because if you have a look at all the data structures that are in there, you will find stuff like multimap, replicated map, which looks pretty much like an IMAP, like a normal map, is just fully replicated, which means it won't be partitioned. You have sets, lists, but besides this, you will find queues and topics, which are actually usable for some very basic, PubSub scenarios, if you really need that. So for example, our implementation of Hibernate second level caching, one of the implementations stores the data in local maps, but uses the Hazelcast topic to distribute updates to other local caches used by other applications, so that you can avoid unnecessary network trips. There's a first question. The first question is, isn't it frustrating? A developer may not expect any network calls while working with map. And this is a really good question. This is a really good question because this is actually something that you need to really be aware of. So if you're working with the cluster, if you are working with a client, obviously you don't need to expose the Java util map interface. You can use with our interface, which kind of suggests that it's actually there are network calls happening. I wouldn't say it's frustrating, but you need to be consciously thinking of network calls if you are working with some applications or integrations that are happening, the interactions that are happening outside just a single JVM. In most cases, if you work with Hazelcast, using in Spring, with Spring caching, with Quarkus and others, probably you won't be seeing Hazelcast as a map. It will be somehow integrated in the ecosystem or in the framework itself. So quite often you rarely work with the map itself. But data structures is just the beginning. Okay, there's a set list. Okay, that's boring. But now imagine, let's go back for a second to this slide over there. All the data is distributed among multiple machines. So imagine a simple use case. You have a map and you want to iterate through, let's say, all the entries and change them somehow. So if you would do a map.forEach, effectively, it would iterate over all elements. But hey, those elements are distributed. And if they are distributed, it means there will be quite a lot of network chit-chat happening to get all those elements to one machine and iterate over them. Sometimes it can be not possible. Imagine you have 100 nodes and each has 100 gigabytes of data. Sometimes it's just not possible to take all that data in one place. This is where the real in-memory computing starts. So for example, in such case, we really don't want to do this locally. We really don't want to do any form of computations. We don't want to aggregate. We don't want to process this data locally. What we would like to do is we'll tell you, cluster, you perform this on your data. And this is where tools like entry processor or aggregations come into place. You implement our custom interface, send it to a cluster, and this job will get performed and each node will perform this data on the data they own at the moment. And this is where it becomes really beneficial for Java developers to play with, so that Hazelcast is written in Java. Because you can write a simple Java code, send an entry processor to a cluster, and then perform all the computations by yourself. It would be a bit less convenient if you worked with other languages, but with Java, it's really simple. So if we can process our data on the cluster itself, it's also possible to execute some arbitrary methods and pieces of code as well, if needed. Same with aggregations and form of accumulations. Imagine you want to calculate the sum of all salaries of some employees, and the employee data is stored in a cluster. You don't want to do that locally. So you write your own custom aggregator implementation, you send it to a cluster, and you get a result as a response. And you know that this will be performed efficiently on the cluster itself by Hazelcast, not by you, saving a lot of network traffic. So in this case, again, you need to be aware that even if you are interacting with a distributed map, it will work. The normal methods from a Java utility interface will work. But if you want this to perform, you need to be aware that probably, just like interacting with a normal database, it's always better to do joins and other operations and other groupings on this, let database do this, and not just do a huge select and join of the data manually by yourself. The same applies here. But what's more, you can also do queries. So let's say you want to just grab employees that are active and below 30. There's no need to fetch all of them and filter manually. You can perform the same. You can let the cluster filter the data for you. And this is where we slowly reach an interesting point here, because this is the point where we need to review the basic constraint in the world of distributed systems. If we have multiple nodes talking to themselves, exchanging data, we have three properties: consistency, availability, and partition tolerance. And the trick is we can have only two at the same time. And this is very important to understand because in Hazelcast you can have you can make a choice. What do I mean? Look, imagine you have two nodes. Normally they are able to communicate and everything is great. But once the communication is lost, once someone, imagine you deploy somewhere in AWS, Jeff Bezos walks around in a data center and kicks a cable out from a machine, and there's no connection. Once there's no connection between two nodes, you have a choice. Those nodes can serve outdated data or don't respond at all. And usually it's the choice that you need to make at some point. The Hazelcast by itself, if you look at the data structures, IMAP, IQ, and so on, they are AP, which means they favor availability over consistency in general. However, on top of the system, we have something called a CP subsystem, which is pretty much something that prefers consistency over availability. And you can find implementations of logs, atomic counters, and similar, and they will provide you have guarantees that it will be consistent. And this is based on data and Jepsen verified. However, keep in mind that there is a trick, if you remember about that, you need to be running at least 3 members to be able to use CP. Because if you have only 1 member, well, if it dies, there's always a consensus. If you have 2 and 1 dies, or just the network is cut, there will never be consensus because you have 2 equally competing parties. But if you have 3, you can have a majority, 2/1. So in the CP subsystem, you will find stuff like semaphores, countdown latches, atomic reference, atomic long, and distributed implementations, all the stuff you would find in the Java util concurrent. However, keep in mind that this is not something you should be using on an everyday basis. This is something that's for very niche applications, but it's worth remembering that this actually is there and it works. But this is just the beginning. This is just the base. So as you can see, we have a distributed cache, distributed in-memory store, which can actually run expensive computations on the cluster side and not by ourselves. It features quite an interesting data and a CP subsystem and a Raft-based CP subsystem, but that's not all. The interesting parts start now. So you will find that these implementations of a ring buffer, ring buffer is a form of circular linked list where if you go over the size of a data structure, it will start overriding the oldest elements. So this can be pretty useful in some interesting scenarios. But imagine a different scenario. Imagine that you have a huge number of nodes with huge number of data. And imagine that you would like to compute the number of unique elements in the whole data set. But it would be really, really expensive to calculate. However, there are probabilistic data structures like HyperLogLog that actually can do this with a huge accuracy using just a small memory footprint. This obviously doesn't give you an exact answer. It gives you something that's really, really close to the actual value, but it's very, very cheap in comparison to actually calculating an actual number of unique elements manually. So this is stuff that actually starts mattering at scale because it's easy. If you have a small data set, then everything will work. Anything will just work. But some solutions, as the scale grows, they don't work anymore. And this is a good example because calculating the number of the cardinality of such a huge data set is something really expensive. But probabilistic data structures are here to help you. Another interesting issue is, for example, an UUID generation. And this is where Flake ID generator can help in. which gives you guarantee that it generates ordered and cluster-wide unique identifiers for the whole cluster. This is not so obvious, that it might be not that easy, but having something like this is actually quite convenient. But that's not all. Imagine, as we covered in CP Subsystem, there's something like distributed implementations of atomic counters, which are consistent. However, in order to be consistent, they require constant communication between all the nodes that are in there, in the cluster. However, there is a concept of CRDT, which is a conflict-free replicated data types, which is something that kind of can give you the correct results as well, but even when there is no connection between nodes, because the potential conflicts can be automatically resolved. And in this case, you can find a positive-negative counter that can be used as a conflict-free implementation of an idea of an atomic long. So this is all that you can find inside. As you can see, this is quite specific, and this is not probably something you should use in your everyday job. But still, it's great to actually have a look at how they look inside and what can they help with. Because learning those concepts, understanding them internally, seeing how they are implemented on top of Raft, for example, that's a huge value for you as engineers. And hopefully one day you could solve a really difficult problem using that one day. However, that's not all, because we've had a look at the core Hazelcast itself, but there is also the whole ecosystem that's built on top of that. So for example, you can use Hazelcast with Hibernate as a second level cache, which means that, and you have two options. You can either use a Hazelcast and use an IMAP, distributed map, to keep all your entities, or you can keep them locally or in each application and only use Hazelcast to distribute updates of invalidation messages between different nodes of the application itself, depending what's your actual need. But that's not all. Let's say you really don't want to interact. Let's say you're working with Spring and you don't really want to interact with IMAP and map and so on, and aggregators and other stuff and predicates. There's an integration with Spring Data, which looks as any other Spring Data integration, where you can use annotations and to write methods, write queries inside methods to actually obtain data, exchange data with Hazelcast. So if you are using Spring Data, this is an option as well. But that's not all. We've recently written a Quarkus Hazelcast client, which is actually, again, I mean, as much as integration with a framework is kind of expected how it could look like. There's nothing extraordinary there. However, Quarkus is fully integrated with GraalVM, which means that you can actually use our extension to generate a native image of an application that connects to a Hazelcast cluster. And this now is blazingly fast. So it's definitely interesting to check out if you haven't checked out Quarkus itself. But that's not all. We have quite interesting integration with the Tomcat Session Manager. So imagine you are scaling your application. You have a few Tomcat instances, but each of these Tomcat instances is keeping some local data, the session data. So if an instance dies, and let's say the client, another HTTP request connects to a different one, it will be noticeable from a client side. However, if you can store all your HTTP session data in a Hazelcast itself. In such case, all the session data is held outside the Tomcat itself. So if an application dies another Tomcat can seamlessly access the same session data that's stored in Hazelcast itself, which gives a very seamless experience from the client side, from the HTTP client that's actually issuing HTTP requests to the cluster, to the Tomcat application itself. You can find something similar in Apache Shiro as well. So, but Shiro is a bit more than just a session clustering. It's basically a security framework, but actually internally it uses Hazelcast to store the data. Another interesting one that's on the way is an Envoy proxy. So, so there's an integration with Envoy coming. It's not yet merged, so this is something that you can expect in a near future to appear. But that's not all. There's quite interesting stuff happening on the cloud integration side. There we have special plugins that allow you to perform auto discovery inside AWS, GCP, Azure, and so on. However, the interesting part is that you have also zone awareness. So if you are after high availability and multi-zone availability, because there's also some extra support that you can get from that. So you can make sure that Hazelcast clusters are formed from instances spread all over the various availability zones in various clouds. However, if you are overwhelmed and don't really want to configure things on your own, you can access cloudhazelcast.com and pretty much pay us for dealing with all of that and treat Hazelcast pretty much as a service. There's quite a few interesting enterprise features available out there. So for the big clients and big use cases. So imagine your requirements when it comes to high availability are really strong. So for example, imagine that you want to be really sure that your application can actually serve data continuously. So what some clients actually want, they would rather have two clusters, with one being actually just a failover to be used just in case something happens. So if something goes wrong with the primary cluster, a Hazelcast client can seamlessly switch to the other one and pretty much continue operating like nothing happened. And this is what some huge production scenarios require. But it's not more. If you are a big financial institutions, like for example, JP Morgan Chase, you probably have a lot of clusters. You have one cluster in Paris, one in San Francisco, one in Tokyo, a few in the US. But you still want to keep them in sync somehow. So for example, you can have a situation where your client travels from Tokyo to San Francisco or to Europe, and you probably would them to be able to see the data that's actually correct. So this is where one replication kicks into. This is how clusters can actually replicate data. Different clusters can replicate data and sync data between them. So if you have a huge deployment which consists of multiple clusters all over the world and you want to keep them in sync, this is where you would use one replication. But that's not all. As I spoiled a few minutes ago, there's also quite an interesting enterprise feature, along with the integration with Intel Optane DC persistent memory. What Optane DC is effectively just a RAM that can operate in the persistent mode as well. And if you use features like hot restart or HD memory, you can fully benefit from that. So hot restart is probably, as you can expect from the name, Hazelcast node itself can actually drop all the data it has to dump all the data it has into a persistent memory, restart and read it back there, providing a very fast restart experience instead of just starting from scratch and repopulating the node for itself. Another option, interesting one, is HD memory, which is an off-heap store. What if it's the latencies and generally the GC overload is not acceptable for you? In such case, you would like to keep all the data outside the jurisdiction of a garbage collector. You would like to keep them in the off-heap store where the garbage collection doesn't really happen. So that's another feature that you can use to actually squeeze the most from your Hazelcast deployment. When it comes, and we are pretty much getting close to the end. And when it comes to the future of the tool itself, there's one great endeavor we are undergoing right now, which means we are implementing an SQL engine, a real SQL engine for the Hazelcast itself. It will be already available in the 4.1 as a preview, so you can play around with it and have fun, but it's not yet production ready. So no longer a simple SQL predicates, but a full-blown SQL engine. But that's not all. This is pretty much what we've been speaking of. So Hazelcast as a whole company, we all specialize in performance and in-memory computing and stream processing as well. So what you've seen here pretty much is just the part concerning the in-memory computing and storing and playing around with data, but that's not all. There's a missing piece of a puzzle here, which is a streaming solution, which allows you to perform processing real time on incoming data. So this is where the Hazelcast Jet comes into play. Hazelcast Jet is something totally different. It's a separate product which can read data from Hazelcast, messaging, databases. It can do CDC with Debezium. It can read files, application connectors, social activity, IoT, or whatever else you implement by yourself. It can feed the data in real time, ingest it, transform, combine, play around with that in real time. You can then apply some machine learning and magic to it, and then do something with the data. So one of the telecom use cases, imagine you are stream processing a GPS data from your users. Imagine that there is a user that seems to be driving towards the border, the country border. So this is maybe a good moment where to send such a person a roaming offer. So real-time stream processing is really good for scenarios like this, or perhaps even COVID contact tracing as well. I did never see a solution based on Hazelcast on stream processing for that, but this is probably a scenario where it would fit really well. And if you have a look at how this looks like, this might look like pretty much working with the even a Java Stream API itself. However, keep in mind this is not Stream API. This is not happening in the here where you write it. This is pretty much a job definition that you deploy to a cluster. This is performing the job for you. So this is not a jet talk. I just want you to be aware of that. But what I really would like to have a look at is that teams, we are all actively working on making our design documents and architecture public. So if you really want to get to know the tool better and see why certain things are done the certain way, you can go for the architectural design papers and have a look and seek answers there. However, I didn't come here to teach you the basics of Hazelcast. I didn't really want to show you the most basic stuff, because if you really want to do this, you can go over to training.hazelcast.com and learn those stuff by yourself, because there is a constant effort that actually to produce training content that you can use and learn by yourself. So you can view this as a simple courses that you can use to just learn the tool. We are also very open source. We are open source and open source friendly. So if you'd like to contribute, but you have no clue where to start, find this guy and ask him, and he will help you. So thank you very much. And 40 minutes is not a lot of time, but I hope I managed to at least paint the picture about what we do, why we do it, and where are the interesting bits. And I hope you liked it. And I hope you will at least have a look. You can, if you want, you can find me on Twitter, you can find me on my blog, and I'm always there to answer questions that you have. So thank you very much. And I think we have some time for questions. Let me have a look.
Thank you for your talk. Indeed, questions.
Okay, so the first question. I understand Hazelcast is serverless and is peer-to-peer. What are the other features within the Hazelcast architecture that makes it high performance? I believe this was partially answered while I was showing multiple features all along the way. High performance, this is quite a broad statement. So let's try to narrow it to just a few parts. If you have a look at the performance of a single node by itself, you have features like that allow you to speed up the restart, which is the HD hot restart store. There is stuff that allows you to avoid extra latency, for example, by storing the data off heap. The tool internally is designed with performance in mind. We are also experimenting with stuff like thread pinning, but this is not yet released. So if you have a look at the internals, this is all written with performance in mind of a single Java of a single Java process. However, you can also have a look at the performance at scale. So if you have a look at how communication is happening between nodes, and we try to save as much as possible when it comes to the network calls that are happening between members. So for example, if your client asks, if you reach one node, but the data is a different node, it won't just forward it to a different node, take it back and take it back for you. That second node will send the data directly to the client itself, saving some time. But if this is not enough, again, you have the in-memory computing tools like entry processors, aggregations, predicates that offload all the work to the cluster itself, making it faster. And actually, it's possible at all, because not all you can do from a single Java application. Probably you wouldn't like to download 100 gigabytes of data over wire only to do a simple filtering over them. This is something that the cluster should be able to do on its own, just like you would expect from a normal database. However, the main benefit of Hazelcast, as you can see, besides caching, is the high availability it provides. So as you can see, all those, besides the raw performance, you wouldn't just use Hazelcast, as a simple in-memory single node element to get better performance. In such case, it's better to use a dedicated in-process cache like Caffeine. The power comes from the high availability you get, the power to work on huge volume of data fast. This is where it comes. I hope it helps. We still have a bit of time. There's another question: when to choose Hazelcast and when to use EHCache? I believe I think I answered this partially. As you can see, Hazelcast, use definitely Hazelcast when you are thinking about distributed computing, when you want high availability, and if you want to offload some work to the cluster itself. EHCache would be more suitable for quite a simple scenarios, but I believe that the previous answer answered this as well accidentally. Do you have any more questions?
Yeah, I think that we're pretty tight on time, and that was the last question. Actually,
okay.
You can always find speakers by their Spine platform and DM them if they're there. Thank you for your talk. It's really interesting, and I have an announcement because of technical reasons. Our next session is a pre-recorded video, so I need to announce it on your sessions. Sorry. So next session will be a session by Mark Heckler. He's a professional problem solver and Spring developer advocate at VMware. He's a conference speaker and also a Java champion. He worked with key players in manufacturing, retail, medical, scientific, telecom, and financial industries, and public sector as well. And his talk will be about tuning messaging systems to their greatest performance. So that was the announcement.
Okay, so thank you very much. Enjoy the next session.
Yeah, thank you. See you.